So you should be able to see my screen. Perfect. So welcome to my talk on the applicability of annotation-based source code modification in Kotlin. My name is Markus Weninger. I did this work together with my bachelor student Daniel. And first of all, please let me give a motivating example. So imagine we have a bank account where we have a current balance, how much money is on the account, and we can withdraw money from that. And what we mean with annotation-based source code modification is we would like to be able to add annotations to, for example, fields, properties, or parameters of our methods, and then during compilation or at runtime, certain checks, for example, could be added. So when we create a new account, that the balance should be positive or zero, or that when we withdraw a certain amount, that the balance is still positive. And this should be checked in every function that works with such an annotated property. So this is what we understand it's annotation-based source code modification, and we have a look at that in Kotlin. So how can we achieve that in Kotlin? How does compilation work in Kotlin? So we have Kotlin source code, and typically we get Java bytecode out of it. But Kotlin is multi-platform, so we can also get JavaScript code from Kotlin or iOS code and some other compilation targets. Kotlin inside uses an intermediate representation to generate all these target codes. And now the big question is, when we see an annotation, how can we react to that annotation to modify the source code? And in the best case, not only for one specific target, but for all our targets. So which ways exist in Kotlin to process annotations and to modify the code? Generally, there are 4 different ways how we can do that. The first one is how we can process annotations. There is KAPT, which is the Kotlin Annotation Processing Tool. This was the first tool introduced to work with annotations in Kotlin. Then there is KSP, which is the Kotlin Symbolic Processing. There is our custom compiler plugins. They're extremely versatile and can attach to various phases in the compilation process. And then there are load-time approaches that do not work during compilation, but when the program is run. For example, we could use a custom class loader or Java agents, which most of you are probably familiar with. I will not talk about KAPT because KAPT is already in maintenance mode, so no new features will be added. They try to keep it working, but they will not do much more there at JetBrains. So I would start with KSP, Kotlin Symbolic Processing, where the basic idea is that we iterate over symbols. We do not have the complete us there, and we generate new code. So I brought an example with me. What we have to do is that we have to inherit from symbol processor, and we have a process method where we have a resolver. This resolver is there so that we can find things. We can, for example, use the resolver to find all symbols that are annotated with a certain annotation. But we could also say we want to find all files, we want to find a function by its name, and so on. KSP revolves heavily around the visitor pattern, so we can write our own visitor where we can visit about 25 different things, properties, functions, classes, and so on. And these visitors typically have the code generator passed into them, so we can create and write to new files. And then we apply our visitor, for example, on all our annotated entities and generate something out of those annotated entities. What is the big problem with KSP? Because the code that we can write is quite straightforward. The big limitation is we only have code generation, no code modification. So we cannot modify the program we are looking at. We can just create new files. And there is no analysis on expression level. We have no information about the statements of a function. We know which parameters go in, we know which types go out and stuff like that, but we have no information about the content of the statements. So that's where custom compiler plugins come into play. They are great. They are super because they can provide additional operations, including modifications, in various compiler phases. So Kotlin's compiler is split up into multiple phases. You do not have to look at the whole picture. I will guide you through the most important parts. On the front end, first we have the lexical analysis and the syntax analysis, so we get a typical AST. Then this AST is enriched with semantic information, so we have a front front-end intermediate representation where we perform the code analysis on, or where Kotlin performs the code analysis on. And then, independent on which language we compile to, JVM, iOS, or the web, we have a common backend where optimizations are performed on an intermediate representation. And then only after these optimizations have been performed, there is a last target-specific backend, for example, a JVM backend or the JavaScript backend, where the final translation is performed. And the cool thing about this compiler structure is that we have different points where we can attach to and add our own plugins to modify what is happening during compilation. So there we have at least 5 points, and for those 2 points, so in the common backend, we wrote an example which is hosted on GitHub because there are really nearly no examples out there, and I want to guide you shortly through this little example. So we have, again, a visitor pattern, and we are currently in the method visit function new, so we visit the function for the first time. And we can get the body of that function. If you remember the example from the first slide, what we want to do in the function is, if a parameter is annotated, we want to generate verification code that the parameter is in the correct state. So what we do is, and we can do this very easily, we generate a new block, a code block that was not there before in the source code, by having an IR builder. So we build intermediate representation blocks. And then we can just iterate over every parameter of our function. Then we can check the parameter if it has a certain annotation. So we check, is the parameter annotated? And then we can generate IR nodes, which is hidden in this generate verification function call method that we have written. And with this little plus in front there, we can add this IR node to the block that we just generated. So we can add completely new code independent of the target language, and then when we have generated all verification codes, we have this one block of code, which would then say, this should be the first statement in our function. And that's all we have to do to have new code in the existing code. What is the main limitation here? There is nearly no documentation. Plugins, compiler plugins, are typically used internally at JetBrains to develop stuff, but you can do your own. And so our references out there on GitHub, you will have a QR code in the end if you want to have a look at it. And just for the sake of completeness, I also want to talk about load time approaches, which are approaches that intercept classes when they are loaded. So typically we have some class that is stored in a class file. When it is loaded, we want to instrument it, or we want to weave code into it. This is often supported by libraries such as JavaSys or ASM. So first of all, we have to find the location where we want to add source bytecode to. Then we have to generate that bytecode. With JavaSys, this is really easy because you can provide the code that you want to add as a string, and the bytecode is automatically generated for you. And then we just have to insert it, which is also a one-liner with JavaSys. So this is really easy, and that there are a lot of examples out there. But the limitations here are this slows down application start because the code is modified on every program run, not only once during compilation. And this only works for JVM, so there is no automatic multi-platform, which is a big minus if you want to go multi-platform. So to summarize the advantages and disadvantages of the 4 different approaches, KAPT, KSP, custom compiler plugins, and load time approaches, is KAPT has its advantages. You can reuse annotation processors that you have already written for Java. KAPT is, you can imagine it as a wrapper around the original Java annotation processing tool. KSP is Kotlin idiomatic. That means it knows about Kotlin-specific things like initializer blocks, data classes, properties, and so on. Things that did not exist back then in Java. It is faster than KAPT, nearly double the speed, and it is multi-platform. Custom compiler plugins have the same advantages as KSP, but are still more versatile. And and load time approaches are easy to implement, have good tool support, many tutorials out there. But we also have disadvantages. KAPT has a lot of them. It is slow, no multi-platform, does not know about Kotlin-specific things, and code modification, the thing that we focused on, is nearly impossible but it is possible with a lot of hacky and tricky, dirty hackarounds and workarounds. KSP has no code modification at all, only new code generation, and no analysis on expression level. Custom compiler plugins are very complex and really lack documentation. I really hope that there is something happening in the future now that K2, the new compiler by JetBrains, is introduced. And load time approaches slow down the startup, are not multi-platform but JVM specific, for example, and also do not know about Kotlin specific stuff, but Java agents have been written for Java, but can be used with Kotlin. Yeah? So the main takeaways, I tried to make it as fast as possible since we're a work in progress paper. We have 3 different compile time approaches, KAPT, which you should not officially use anymore, KSP and compiler plugins. You have load time approaches like custom class loaders or agents. They perform transformation on the JVM level, on the bytecode level. Compiler plugins are really cool, extremely versatile, but really complex. JetBrains, if you hear this talk, please provide documentation there. And for future work, we have planned to study more how Kotlin annotations are currently used. So a GitHub study how annotations are used there. And what would be really nice is to have a library somehow similar to JavaSys to provide source code as a string and get IR nodes in the compiler plugin that you can plug into your existing code. So code string to IR. So my name is Markus Weninger, and there is a link to our repository where we have a reference implementation for the compiler plugin and a Java agent that can modify existing source code. Thank you.
Thank you, Markus. Now, part of our goal with the work in process papers is not only for you to ask questions, but if you have feedback or ideas to offer the work in progress, feel free to do that as well. So we have time for a couple of people to query or comment.
Questions from my side to the audience. What would you probably use? Do you have ideas where you could use compiler plugins in your work? Do you have ideas? What could you modify at compilation time that you would like to have automatically in your source code? Do you have any ideas? Do you see applicable fields where you could use source code modification in your work?
Well, I have certainly used approaches like this to try to add hooks for, say, transaction-oriented processing, or for persistence, or for distributed system calls, that sort of thing. So a kind of extension of the semantics of the underlying thing by rewriting.
That's true. We are thinking about performance monitoring, for example. So you could add certain code and hopefully hot paths to see what happens. Any more input from the audience? I saw some more hands on the right-hand side, I think.
Try to use the mic so that the folks at home can hear. This is being streamed.
So anything related to, for example, allocation of objects, tracking lifetimes, an extension of what Elliot said, like calling, for example, native code. This is all very interesting points that we really need to sometimes dig into the compiler to actually inject phases into compiler to add nodes that will basically call our profilers. Having like a tool that allows us to do that without having to dig into the compiler would be amazing.
So a tool that can summarize what is happening in your program without having to look at it yourself.
Sometimes you use JavaSys or even ASM, but sometimes you actually need deeper information of what's happening inside the runtime, and sometimes it's easier to express that using IR nodes.
Yeah, so I can discuss this with a bachelor student who will also do a master thesis, so probably he will listen to this talk and take in some of your advices or suggestions. Thanks.
Okay, thank you very much, Markus.